over really, I'll take your questions in a second. 3 basic circuits that I didn't talk about with op-amps that are very important. Show you 2 to 3 different circuit realizations and then take questions about the homeworks, okay? And I'm going to try to do this efficiently. Please be attentive here. I know I'll get to your questions. I don't want to get hung up with them right now. All right. So first thing I want to talk about is feeding the positive things on. Still on. Projector. Anyway, first thing is feeding the positive terminal. Some people wondered about this last time. I actually got a bit confused doing this, and I apologize to all of you. So I want to make sure you follow me on this. If you have an operational amplifier as such, you don't know what it consists of and why certain things are the way they are. That's the negative, that's the positive terminal. Now you can feed the positive terminal right there with a voltage, call it Vn of T. That's allowable, and it's done. As a matter of fact, who came to me with that op-amp design last class? See me after class, I can help you with that, if you want. I'll show you this. Then you're going to have some R1 here, and some R2 here. This will be V out, and this is going to be grounded. This is another common circuit. I'll try to be neat about this. This is Vn T right here. All right, now work with me on this. You'll see why there's no inversion here. First, if this is ground, that's 0 volts, right? That's 0 volts, that means VI is here, the input voltage, which means VI is here as well, which means this current is simply VI over R1. We agree on this? Everybody? Can you see it the far back there, guys? All right, now, if that's the case, how much current comes out of the negative terminal?
0.
0, always. And when I ask that, it'll stay with you. People have current coming out of there. In the real world, there's something called a trickle current or a leakage current that you'll have to deal with for non-ideal op-amps. Don't worry about this. These work what I'm showing you pretty much all the time. Not for every situation and not for high frequency, but for most things. Now that means all the current is coming this way, right? If I just call this I1, I know that this voltage is simply I1 R2, right? Or I can say that this voltage right here is just going to be equal to, call it V2, equal to, and that would be V in times R2 over R1. Do you agree with that? I'm calling it V2 there. That's a little, y'all follow me? Show of hands here. Now, what is the output voltage? Well, you know the voltage across here is going to be VI over R2 plus R1, right? But that's not the only voltage. If you start at ground right here, because this is always measured with respect to ground, I get an increase of VI, so I can say that V out is equal to VI plus this voltage, or plus VI times R2 over R1. Or I can say it's simply VI times 1 plus R2 over R1. And therefore I can say that V out over VI would be the transfer function. And that's simply equal to 1 plus R2 over R1. Here, there is no inversion at all. And you can calculate the values of 1 plus R1 over R2 to give you any gain you want. You follow me, class? That's a non-inverting. That's not as common. There's going to be things you learn in electronics. Why? Almost, I won't say almost always, most of the time they feed the signal through the negative terminal, and that comes later, and I can't get into that here. That's electronics. How many of having Dr. New's class, right, in digital? I don't think he teaches analog. I'm not sure who's teaching it. But when you get into analog, you'll see about this. This is called the beginnings. The inputs of this is a differential amplifier. How many have had differential amplifiers? How many have had analog in here? Anyone? All right, well, then what I'm telling you is completely foreign. It'd be like telling a blind man from birth what sight was. There's no use doing it. There's no basis for understanding, so I won't even go there. All right, now the next circuit, this should make sense what I'm saying. Is everybody following me on that one?
Yes. Yes, sir.
Yes?
Just a quick question. So how did you choose the direction of the current, or is it set because of that voltage?
Well, I chose this as a positive polarity, right? If this is Vn here, that's positive Vn here, right? That means if the current is always, what, the voltage on the one side minus the voltage on the other divided by R1. If Vn is positive, the current goes that way. If Vn is negative, the current goes the other way. But you don't care, you define it in terms of Vn. Understand, class? How many do? Vn determines that. All right, I chose the direction going that way because I'm assuming Vn's positive, just for simplicity. Now, the next circuit is called a summer. This one is real important, so write this down. This is a summer. Summer circuit, and usually you'll see this. It's the summation symbol to indicate this. And it's adding things. Now, here's the way it works. I'm going to take three voltages and feed them through 3 different resistors. But all with respect to ground V1, V2, V3. They're all going to be, this is all tied together, and it's going to be fed into the negative terminal, positive terminal grounded, and then here I'm going to have some R4. Just write that down. Remember, I'm assuming all these voltages those are positive with respect to ground, the measurement to ground. Understand? So it's only one terminal that's shown always. That's common. Everybody got that? Now, I could add as many of these as I want in parallel. There's no limit. But for now, 3 is sufficient. Now, what is the current flowing through R1? Just take a look at it. What is this? Well, let's do it better than that. How about if this is 0 volts, do you all agree that's 0 volts on that terminal?
Yes.
Does everybody have that? Mm-hmm. Well, that means the voltage difference is V1 minus 0 over I1. Over R1, or I1 is simply V1 over R1. Correct, class? Does everybody see that? Give me a show of hands. What's the current here?
V2 over R2.
That's right. V2 over R2. What's the current here? All right, now we've got those 3 currents going into a connection. Part of the connection goes into the negative terminal. But what's the thing about how much of that current can go through the negative terminal? 0. It all must go here. That means I1 plus I2 plus I3 flowing through R4. Follow me? How many see this right here? Now, if that's the case, what's the voltage drop across R4?
R4 times all those currents.
Well, VR4, the way I'm showing it, plus the minus would be the current, which would be V1 over R1 plus V2 over R2 plus V3 over R3, right? That's the current that's flowing here times R4. Do you agree, class? I want to make sure you see this. I don't want to fly through this. How many see it? Now, what is the output voltage, though, here? Isn't it really the negative of this, class? How many see that? So this voltage right here is minus VR4. But I don't want a minus, I want a positive. So what do I put in series with that? A simple, inverter with 2 R's, both the same value, connected to the negative terminal. So now I just put a value, it doesn't matter what these R's are. R here, R here, and now this, V out, right here, would be equal to that. It would be equal to V1 over R1 plus V2 over R2 plus V3 over R3 times R4. Now I want you to take one look at this for a second. How many see this first of all? Y'all see it in the back or not? What if I make R1, R2, that should be R2, R2, R3, and R4 all equal to the same value, or 1 for that matter? What does that become? It sums up the voltages, right? It just adds them up. Now listen, I can also get any effect if I want. If I want just V1 by itself, I could have R4 over R1 to be equal to 1, plus 2V2, then I could have R4 over R2 set to 2, plus 3V3 added up to the output. Follow me? Now I can proportionally weigh these, so I can do that as well. Does everybody understand that? This is a summing circuit. It's very common, and it's very useful. Do you remember when I showed you how to do realization? I showed you those blocks where you had summers. How many remember that? This is the electronics that you would use to realize that. Got a few more things to show you. Are you with me, class? All right. This is practical. How many work with op amps in labs? One? Well, you're going to, because this is the one thing. I mean, resistors, inductors, and capacitors admittedly are the first things you work with. Then, how many have worked with transistors? Not many, all right? That's usually the next one. Right after that, it's operational amplifiers. Almost always. And you get to design all sorts of stuff and analyze things. But this is a really important thing. Yeah?
Like so far, the op amps, the two terminals always share like the same voltage. Is it always gonna be like that?
The voltage difference between the plus and the minus is 0. So whatever voltage is at one terminal is at the other in the ideal op amp. That's the way it works. And that's the basic law. There's no current into it, no voltage across it. And it's done by all sorts of feedback and things like that that have to do with the internal workings of the electronics that I can't get into here. Now, another thing.
How big is an op amp?
What you're asking is something that scale-wise, and the chip itself is visible. I mean, but how many op amps are on that chip? I don't know. You can probably have 15 op amps on a single, 32 or 64 prong chip. I really don't know how many can be on there. Op amps themselves, you can't really say in terms of size of the operational amplifier. You're saying size in terms of the chip that holds it, because the chip itself is the thing you stick in when you do any work with it. How many of you've used 740? You showed me the 741, right? Isn't that about not even an inch little chip?
Tiny, smaller than the counters used in Midnitronics.
It's real small, but the thing about it is usually you don't have just an op amp. You're going to have everything else, including microcontrollers and stuff, on these chips. So the operational amplifier is one facet of it. All right, that's a summer. Next, I want to show you how to realize some of the most common transforms. And I want to tell you one other thing too. These transforms in S, when we let S, S is equal to sigma plus j omega. When we let it just become j omega, then it becomes a transfer function in the frequency domain. And that's a filter where you can get either gain or loss or customize things. And that's what I was driving at with mentioning Professor Bose and his speakers. Understand? So I'm not there yet with you, but you'll see it, I bet. So suppose I wanted to realize this circuit. I have H of S equal to some constant A over S plus small a. I'm just putting it down like that. And A, capital A, and small a can be anything. But if I want to realize that the circuit that I know, and you do too from experience, that'll do that, is this. If I take an operational amplifier, and I simply take the first impedance, and I make it a resistor, and I'm going to call it R1, feed the negative terminal. I always feed the negative terminal. I know we don't have to, but I'm going to do that, so you can write me nasty letters. But that's the way it's always done. Here's my VN, and then up here I'm going to put two values. I'm going to put R2, and I'm going to put C right here, which means the impedance of that is 1 over CS. Let me just put that in there right now. And here's my output voltage right here. Understand, class? Everybody? I know that the ratio of output impedance to input impedance, or I should say this impedance to this impedance with a negative sign is the transfer function. Isn't that right, class? So I'm going to go ahead and just say that I know V out over V in would be equal to my H of S, and that's equal to this impedance minus that actually. Let me do one more thing. I'm going to go ahead and go the whole 9 yards on this one. I'm going to go ahead and put the inverter here. Just call this R, around that. Now we can say V out over V in here would be equal to H of S. And the reason I did this is so I don't have the negative to worry about. Follow me, class? Show of hands here. Everybody? These two are identical. The only thing it does is take that and makes it negative. Since I know it's going to be a minus there, I just want to get rid of. So this is going to be the output impedance here, and this is your Z2 over the input impedance here, and this is your Z1. So this is equal to Z2 of S over Z1 of S. Even if they're not functions of S, I'm putting it in there. I don't have to do this, but I'm really trying to bang it into your head that this is a function of S usually. All right, well, the Z2 of S right here, I told you this last time, always do it as 1 over the first impedance, 1 over R2 plus CS, right, 1 over the second impedance. Agreed, class? Then I'm going to factor out simply the C. And the reason is I want the coefficient of S be 1, right off the bat. So when I do this, I get this. I get 1 over C divided by 1 over R2C plus S. Please take a look at that and make sure you agree with that. I want the coefficient on S to be 1. Follow me? Everybody, that's real important. Got it, class? So now I come over here and I say when I take Z2 over Z1, well, that's Z2 and Z1 is R1, isn't it, class? So I have simply 1 over CR1 over 1 over, and this would be CR2 plus S. Now, for the value of A here, if it's very large, I can do one last step. I can go ahead and instead of making this R just R, I can make it 10R or 100R or whatever the scale factor I need there is. How many see that? Because that would simply scale up the output, wouldn't it, class? Give me a show of hands if you do. I don't want to focus too much on minor details. But when I take a look at this right here, I can see that this becomes A right here. Agree? And small a is this. Now the book a lot of times puts a tau there. It doesn't matter. It's a symbol. How many see this right here? Got a question for you. That's for a simple pole, right? I showed you how to do an integrator, a 1 over S, and a differentiator, an S times a function, right? Last time? You know those two. So you got integrator, differentiator, now you have a simple, yes?
The only thing I'm confused about for this one is how you combine your impedances to get Z2.
Well, anytime you have any two impedances in parallel, if you have some Z1, well, let me do it this way. If you have Z1 here, and it's in parallel with Z2, right? And you wanted the parallel combination. You could say that this impedance was Z1 times Z2 over Z1 plus Z2, right? Or you could say it's 1 over Z1 plus 1 over Z2, right? That's what I use. And that's a smart way to do it. Because it may not be 2, it may be 3, maybe 4. All right? One other thing I'm going to say, remember this. You don't use inductors with operating circuits almost ever, unless it's something called if this is going to be something that represents the impedance of an antenna, or if you're getting something called a resonator effect, don't ever assume to use inductors. And the reason is inductors don't work well in microelectronics. All right? With VLSI technology, we can make capacitors, we can make resistors very easily. Inductors themselves in there are a problem. Just remember what I'm telling you. Use capacitors and resistors. So that's a simple pole. Now, here's the question I have for you. That's this, right? What if I didn't want a simple pole? There's some smart people here. I got a feeling they're going to get it in my heart. Suppose I wanted this. I want a double pole. What might I do? How about we put two of these in series, right? If this is the transfer function right here, of this and this, what if I put it in series with another one? How many see that? That would give me a double pole. Wouldn't it, class? Give me a show of hands if you do. Right? Because they're in series. You multiply the first transfer function by the second, correct? If I wanted a triple pole, you would take this and this, repeat it once, repeat it twice, and now feed them all. You all see that, class? Here's the one thing you have to be careful about. The constant A here, it's 1 over CR1 squared, 1 over CR1 cubed, and stuff like this. You're going to have to be careful that you get that value right. I'm just telling you. All right, but that's the principle. How many understand that? All right, so we've done simple poles, double poles, triple poles. Now a complex pole, or something where you get yes.
So does that mean that we need to adjust the A value after?
Well, it depends what the value is back here. I just used, if I put 100 there, or S plus, say, 10 to the minus fifth or something. All right, you have, let me explain why I'm saying that. You have a range of capacitors and resistors usually to choose from. You don't have an infinite, you don't have a continuum of values. So what you do is always get that lower time constant here exact. All right, you make that work. Then up here, you may not be able to make this work exactly. So what you're going to do is, in order to make it work exactly, you're going to scale these two resistors so the effective gain of that will get you the constant you want. That's the way it always works. And trust me, some of you probably have experience with this. When you go to, you have parts you can get. You have when you go to your labs and stuff, you have parts available from the bins, 100K, 50K, 25K, but you don't have 25.058K, right? Not usually. You might have a rheostat or potentiometer or something like that, but even those can be hairy. So what you do is, the things that you need exact, you tie down with RC values or whatever it is, or RLC values. And then the things that I consider scalable, now you can figure out some way to get like a resistive bridge or something like this to get the scaling effect. All right, always worry about the amplification effect last. Get the time constant first. And you'll have a lot of experience with that later. One of the biggest things that I remember in labs that I had, a lot of the parts we were given, we had a shop manager, a guy who would work behind there. If you wanted parts, you have to get them and then you return them, and they didn't work. So the first thing I always assumed is they didn't work. Second is that the values that were set on there weren't always the values. So I always measured the values. I don't know if you have that same problem, but I learned from experience that capacitor is not necessarily good. I learned transistors don't necessarily work, and I learned that resistors that say they're 100K may not be due to whatever reason. So I always measure if it's important beforehand. All right, now, here comes the next bunch of fun. So I said I don't use inductors, but we have to be able to get something where we can we can actually synthesize a pole like this. H of S is some A over S squared plus, say, small as plus B, and this could be complex, that could factor to have complex conjugate poles. We've already done what? The double pole, so that doesn't matter. It could be complex conjugate, or it could be two single poles, right, class? Depending on factors, if it was S plus, say S plus tau 1, S plus tau 2, those are two simple poles, you get A over S plus tau 1 plus 8 over S plus tau 2. Those are two simple circuits that you use a summer to add together, correct? If you have a double pole, you just saw how to do it. But what if you have complex poles? Follow me? Well, if you have complex poles, you know this thing is going to actually come out as A over, then it's going to be S plus A over 2 squared plus, and then you're going to have the term, it's going to be what? B minus A over 2 squared right here. Remember how you get that? You complete the square class, right? If you have complex, we always use what? We always get in the form of a damped sinusoid, right? It was e to the minus at times either a sine of omega naught t or a cosine of omega naught t or a combination of the two. Correct, class? And they damp. How many remember that? I don't want to spend a lot of time on that, but that's, so how do you realize this, right? Watch. Here, we'll take an operational amplifier. Here's your Vn. Now I'm going to put some R1 here and some C1. Now remember, these are in series. Then up here, I'm going to put it into the negative terminal. Up here, I'm going to go ahead and take some C2 and some R2. And when I look at this, I can see that the impedance of this, Z1, is equal to R1 plus 1 over C1S. Does everybody agree with that? They're in series, correct, class? Can you all see it? I worry sometimes. Can you really see it? And here, this is what? 1 over R2 plus C2S. Correct, class? And I told you to factor out the C2 on this one, right? And we'll take care of that C. Matter of fact, I'll tell you what, yeah, I'll do it on both. This is going to be 1 over C2 here divided by 1 over C2R2 plus S. That's that impedance, call it Z2. This impedance, Z1, will be equal to, now, if I factor out the 1 over S here, then I get, I'll tell you what, I'm going to leave this one alone because I can explain it just with that alone. All right, now with this, and I'm also going to go ahead and put the inverter right in front of this thing. So I have R, just R here into the negative terminal. Ground that, R here, and they come out, and now this V out over V in, the transfer function, is going to be this, so it's going to be 1 over C2 divided by 1 over C2R2 plus S, and it's going to be divided by this. Then it's divided by R1 plus 1 over C1S. Can everybody see what I've done here, class? I've simply divided that impedance by that impedance. I'm sorry I'm a little tight in the corner. Are you with me? Give me a show of hands here. Now what do you see happening? Well, when I multiply these through, I'm going to have a power of S and a power of 1 over S as the range, right? Agreed? I can multiply top and bottom by S, so it's S squared down here plus some constant times S plus another constant and S on top. How many see that right there? Now at that point, what you can do, right? With this form fit, boy, this is going to be one of those things. For this one, when I get to your problems, let me just tell you one thing. For this one, I think you're going to get an S squared as the order of the top, S is the order of the top, S squared is the order of the bottom. Here, you can see we have an A, not an S there. Follow me? So what you can do is put a simple integrator in front of it. Instead, you can have this right here. Actually, you don't even need this. You can just take this out and put this as a capacitor here and make that some C3. And now this is going to give you an output of 1 over what? 1 over R times C3S, right? So it's a 1 over S there. Follow me, class? And you can figure out the constant 1 over R C3 to set it equal to 1. So you get rid of that 1 over the S term on top. What I'm telling you is you can go ahead and manipulate these things, and the coefficients are the things you'd solve for and equate them to A and B. Understand, class? And you would have a 1 over S in front. And all these things, you can see they're just permutations. They're getting a little more complicated as we go, but you can realize now any of the S functions, the H of S functions that we have with electronics, with operational amplifiers, capacitors, and resistors, including summers, 1 over S, 1 over S plus A, 1 over S plus A squared or cubed, and 1 over S squared plus AS plus B. Follow me, class? All right, and that's real important. Now, you had some questions, and I'm trying to make time for them. Which one did you want me to do?
32.
Okay. Can you tell me what it is?
It's gonna be really hard to tell you what it is, so can I just show you it out of the book?
Come on. I got it right there, but I gotta have you hold it. Come on. Oh, that one. You got the resistor, and then you got another resistor. Plugs into the negative terminal, right? Hang on to this one. I know, and I got a capacity right here, right? Oh, I'm so stay there. Oh, 2 resistors. Then this goes down. And this one goes. This is R1, R2, and this is V. The end, that goes to the negative. All right, class, he asked me about this one. I know I gave you the solutions. Let me go through this one. This is not a hard problem. The trick is where to start. Now, anytime the output voltage of an op-amp appears across either of these two terminals, that's where you go. You'll notice the output voltage V out appears at the negative terminal. Follow me, class? Doesn't it? How many see this? So that's V out right here. If that's V out, what's here? V out. If that's V out, what current flows there? V out, right? Times SC, right? SC2. Correct, class? How many see this? Please show your hands. Are you with me so far? All right, if that current flows here, how much of that current comes from the positive terminal? 0. That means that current flows here as well, correct? If that current flows there, what's the voltage across R2? It's going to be that current, right? And that current, this is what I call this IC2, didn't I, class? Isn't that IC2 right there? Because it's voltage V naught over 1 over C2S, or C2S times V naught, correct? So this voltage here, VR2, is going to be that current, which is going to be V naught times SC2, that current times R2, correct, class? Are you with me? Give me a show of hands if you are. Now, once you have that voltage as well as that current, right? You got that current right here. You got that voltage. Don't you have the voltage here? What is that voltage? It's going to be V naught plus this voltage, correct, class? Once I have, do you see me? See what I'm doing? How many do? Please. If I have the voltage here, and I know what the voltage here is, then the voltage here is this plus this, correct? Once I have this voltage, don't I have the current flowing through here? It would be V naught minus this voltage times C1S, wouldn't it? How many see that? Right? Now I've got that current and that current. I mean, it doesn't matter if I take this current and this current, but I've got both currents. I can sum them and get this current, correct? Once I have that current, I can get what? This voltage, because V1 would be the total current times R1 plus, and then you could just say, it doesn't matter, plus the voltage here, which is VR2, plus V naught equals V in, and you can solve for V out over V in. If you want to, I'll do it. The book should have the solution, or I should have posted the solution. Does it have the solution to this one?
It hand waves its way through all of the circuit analysis.
Yeah.
Well, they're assuming.
And then it hand waves its way through the Laplace transform as well.
All right, you want me to do it? We'll do it. Work with me on this one. I want to give you plenty of time for your quiz, but if I want to do this one, this is a little tricky. I mean, it's a little trickier, but it starts with the output voltage, all right? So if I'm going to do this, I'm going to go ahead and say that V naught's there, and then this current right here, IC2, is equal to this, which is going to be V naught times SC2. That means VR2 here is equal to that current times R2. So it's V naught times SC2 times R2. That's this voltage right here, right? Now if I have that voltage right there, then I can say, and what I'll do is this, I'll take the current going the other way. I'll take the current going this way. And I'll call this IC1. And I can say that IC1 right here is equal to the voltage there at this point, which is going to be equal to VR2 plus V naught, right? It's that voltage divided by this impedance, which is divided by 1 over C1S, which is just SC1. And you can go ahead and keep expanding. You can say VR2 would be equal to V naught SC2R2, or I can say that V naught comes out in front, and then I have SC2R2 here, plus 1, right, times SC1 would be equal to yeah, that's right, isn't it? Yeah, that's IC1 going up. Correct, class? Are you with me? Now, if I, do you agree with that?
For,
We have to subtract V out.
yeah, for IC1.
Oh, yeah.
C2, C1S.
Let me do this. Hurry. When I take IC1, it's going to be that voltage minus V naught, so it's going to be, and actually, here's what happens. There's an increase in V naught, so I'm going to get rid of V naught anyway. Plus V naught, plus VR2, right, is the voltage there. Minus V naught's on the other side, correct? So the V naughts go away. So this is just going to be equal to VR2, which is that times SC1. So that's going to be V naught here, SC2R2 right there, times SC1, and that's going to be that current. The sum of both of these currents, right, is going through here. Agree, class? So that means the total current going through there is the sum of these two, and I can factor the V naught out in front, so I can say IC1 plus IC2 would be equal to V naught, comes out in front, and then I got SC2 plus S squared times C2, C1, R2, and then it's times R1, and that's equal to Vn. Do you agree with me, class?
Not really.
What's wrong? What don't you see? What don't you see though? You have to help me.
When you're talking about
we've got our IC1. And then, so you're saying they come together at that little junction?
Well, that current flows this way, right? This IC1's
Yeah.
and this current flows this way, right? So aren't these two summed, and that has to be this current?
Okay.
You asked it, right?
Yeah,
So that current plus this current equals the current flowing here, right?
okay.
That current times R1 is this voltage, right?
Yeah.
All right, and that voltage, by the way, that's not total, I'm not done with that. This is the voltage here, right? But I have to add to it what? VR2, right? Correct? Plus V naught, right? Because it's this voltage plus this voltage plus this, or plus V naught. Agreed, class? Work with me, help me, guys. So I've got that voltage takes care of this, plus VR2 plus V naught times SCR2, and that's plus V naught. All equals Vn right here. Let me just do this. That whole thing's equal to Vn. Right? Agreed? Now what I want is V out over Vn, don't I? You gotta get your quiz, so I'm gonna make this short and sweet. So if I take and divide by both sides by Vn, I can effectively do this. Get rid of Vn here, it's V out over Vn, V out over Vn, V out over Vn. Or really I can take this, make a 1 there, and say that this really is V out over Vn here is equal to 1. Now, just listen up. I don't have time to go through all the numbers on this one, but now if I take that and invert it, take 1 over that, take all of this, take 1 over it, now I have the transfer function, do I not? Show of hands. You see it? And then you just use the R's and C's that he gives you to massage it to get it to something factoral. Come on. All right. Everything off your desk. Try to get one open desk between you and your neighbor.